And I'm recording this, so I'll put this on line 2 if you want to go back and review. So,
Are we on film right now?
yes, here's my little camera. Okay, so the product rule. Notice what it says. You can't just multiply derivatives. If you've got two things multiplied, you just can't take their derivatives and multiply them. So look what it says. You take the first function. We've got functions f and g. You take the first function, f, and multiply it times g's derivative. Then you take the g function and multiply it times f's derivative.
Wouldn't that just equal the same thing?
No, sir. It might in some really weird circumstance, but just don't plan on it equaling the same thing.
What does g of x mean in this situation? I know f of x equals the equation, but what does g of x?
It's another equation. You've got two separate functions going on here. So they'll have to give you both functions, and then you get, what if I multiply those functions together?
Okay. So down here at the first question, there are two functions, right? That's what the parentheses mean.
What are we talking about? Yeah, we haven't gotten that far yet.
Okay, I was just see if I can.
Yeah, you got two functions, though. Okay, are we good with that? And notice down here at the bottom of this page, it says generally you cannot just take both derivatives and multiply them. You got to use this rule. And since we're adding, the order doesn't matter. We good so far?
Yes.
Okay, let's take these. I've got two functions. And yes, Wyatt, that's exactly what it means. Now, could I just multiply those out using FOIL?
Yes.
And then take the derivative using the power rule and combinations? Yeah, I could. But let's use the product rule just to get used to it. Because there's going to be some things you're really not going to be able to multiply out. Look at B, for instance. Okay, so what do? The rule says take the first function, so 3x minus 2x squared, times the derivative of the second. Well, what's the derivative of 5 minus 4x? Minus 4. Right? From the power rule. Okay, then it's plus, take the second function, 5 minus 4. This actually takes longer than just multiplying it out with FOIL. But let's do it this way, just for the sake of our broken hearts. Okay, what's the derivative of the first function? So 3 minus 4x, right? If something doesn't make sense, stop me. Okay, so I'm going to multiply negative 4 times this first parenthesis. So I'm getting negative 12x plus 8x squared plus 15. I'm just foiling now. Minus 20x. You're welcome. Lost my place. So minus 20x, then minus 12x, and plus 16x squared. Okay, double check my math. So then I've got 24x squared. So 24x squared, and I can just mark these out because I used them. And then x-wise, I've got negative 12, negative 20, negative 12, so negative 44. And then plus 15. All right, that's the derivative. And if you FOIL the first things, those two functions to start with, you'd get the same thing on that one. So on a test or something, unless it specifically says use the product rule, which it probably won't, then you decide which way is the best. Okay, let me see if I can shrink this. Get it out of the way a little bit. Okay,
I think I forgot what derivatives are. So
well, let's cover that after we get through talking about this.
I don't remember what words are connected with each part.
Short answer is it's the slope of the function at different places.
Like the zenith and the zenith and slopes.
Derivative is that equation where it's like the x plus h.
Yeah, that's the definition of it.
Okay, I'll figure it out.
Okay, so what are our two functions here? And g of x, just to make sure we're on the same page here, is sine x. All right, so what do I do? First function, what's the derivative of sine x?
Sine of 1.
Cosine x. And then I take its plus, and then I take the second function, sine x, times the derivative of the first function, so 2x. So now I've got x squared cosine x plus 2x sine x. And that's my derivative. Now, if you needed to pull an x out for some reason, you could, but that's a perfectly good answer right there. The multiplication rule is so nice. Look at the quotient rule. It makes you work for it. So look what it's saying. You take the second function, g of x, times the derivative of the first, minus the first function times the derivative of the second, and then we're dividing all that by the second function squared. Not the second function's derivative, but the second function squared. And all that's going to work as long as that function doesn't equal 0. The second function, that is. And please read the note down here at the bottom. Unlike the product rule, the order really does matter here. So it's like, but yeah, I mean, subtraction and division, the order has always mattered. So again, we're taking the second function, and the way I remembered it's just like I'm bringing this one up. Second function times derivative of the first, then first function times derivative of the second.
So I guess the function right here, it's one of them is in this. No.
Okay, so f of x is on top, g of x is on the bottom. So what do? I think of g of x coming up to the top, so I'm going to say x squared, this is my second function now, times the derivative of the first. Well, what's the derivative of 5x minus 2? 5. All right, minus the first function times the derivative of the second function. So 2x. Good so far? All that's over, I'll do better, x squared plus 1 squared. Okay. That equals 5x squared plus 5 minus, now I've got so minus 10x squared. I'm multiplying that 2x minus 4x. No, plus 4x because I've got a minus in there. Check me. All that's over x squared plus 1 squared. Double check, am I good? All right, so I start collecting like terms here. So I've got negative 5x squared. I use that, plus 4x plus 5. Now, bless you, I can multiply that bottom out. I can leave it x squared plus 1 squared. It just depends on the context. If you needed to multiply it out, I'm kind of thinking nothing's going to cancel. But if you have the feeling that it might, we can go ahead and multiply it out. So I'll get what? X to the 4th plus 2x squared plus 1. So it doesn't help in terms of canceling anything. Either way, either of those two would be good. All right, let's look at B. I bring that bottom thing up, so I've got cosine times the derivative of sine. Cosine. Let me put the x's in there. Do it right. Minus sine times what? What's the derivative of cosine? Negative sine x. All that's over cosine squared x. Yeah? So on top I've got cosine squared x plus, oh, you're going to love this, sine squared x. Alarm bells ought to be going off. Be glad you did all those identities last year. So I've got 1 over cosine squared x. Depending on the context, I could leave it like that. If I didn't want fractions, what could I say? There you go. Now, before we leave this one, take a look at this. That's a derivative of that thing. It's a derivative of this thing. What is the thing that I circled up here on top? Tangent. So now, without even looking at that set of papers I gave you, you know that the derivative of tangent is secant squared. Right? Okay. Just want you to get your money's worth here. So then it's given us the derivatives for the other 3 trig functions that are not sine, cosine, or tangent that we just figured out. And just take a minute to look at them. Tangent we just figured out. Cotangent, there's kind of a pattern here if you think about it. Always look for patterns in math. I mean, tangent is secant squared x. Cotangent is negative cosecant squared. Secant appears in its own derivative here, as does cosecant. But there's a definite pattern going on there. I wouldn't worry about too much. It's just kind of cool the way some of those things work out. And then down at the bottom it says, oh yeah, the stuff from 2.1 and 2.2, that still applies to all of this too. Those other rules that we looked at. Let's find these derivatives. Now I'm looking at that. I've got two functions I can use. Looks like maybe a combination of the power rule and one of these trig functions. So, and then the addition kind of thing, subtraction kind of thing. So I can take these separately. What's the derivative of x? Think of the power rule. It's x to the first Let's write it out. There's x, right? The derivative is going to be, so f prime of that would be what? 1 times x to the 0 power. So just 1. So I've got 1 for my x, and then cosecant, and it's minus cosecant. Well, what's the derivative of cosecant? We can either turn back here and look. Cosecant,
Cosecant, cotangent.
yeah, cosecant appears in its own thing, so negative cosecant cotangent.
You're not in the right one.
Sir?
You're writing on the wrong page.
Actually, I just wanted to see that
Sorry.
for cosecant. You're good. Okay, so negative cosecant cotangent. So negative cosecant x cotangent x, which gives me 1 plus cosecant x cotangent x. If you needed to manipulate that somehow, you could. I don't see any reason to right now. You know, I mean, you could say, okay, cosecant's 1 over sine and cotangent's cosine over sine. You could manipulate that, but that is the derivative right there. All right, let's look at this one. Oh, we got a division rule, and look at this. We got power rule, division rule, and trig all coming in at the same time here. So how do I do division? And notice, oh, here's something else. If I could cancel stuff out right there, I would. Like if I had an x square on the bottom, I'd cancel those x squares in a heartbeat. It's going to make it simpler, right? I don't. I cannot cancel anything. So I'm going to do the division rule, which says what? You bring this bottom one up. So I've got cotangent x times the derivative of x squared. 2x, okay, good. Minus x squared times the derivative of cotangent. That sounds right. Wait. Is it cosecant squared or just cosecant?
It's squared.
Okay. I'll go with that then. And then we've got on the bottom cotangent squared x. Okay, so I've got 2x cotangent x minus x squared, no, plus x squared, cosecant square x, cotangent square. Can we reduce that some? Yeah, maybe. Do you want to? unless there's something in the problem that would indicate you should, I just leave it like that, unless somebody's seeing.
Well, if you took the sine squared of the cotangent squared x and put it up to the top, it would cancel out them.
Yeah,
But it wouldn't because it would be squared.
yeah. Or I could split the 2x cotangent x apart, put that over cotangent squared x, and, you know, I get 2x over cotangent. You know, I can do stuff like that, which would be what? 2x times tangent x. So you can manipulate these things. Y'all know how to do that. I would just leave it like that. On a test, I'd count that right. Questions? Okay, here's a neat little topic. Now we can talk about higher order derivatives. We've been finding the first derivative. We can take the second derivative, the third derivative, the fourth derivative.
Why would we do that?
I'm so glad you asked. We're fixing to work a problem where that comes in handy. Now, if you did the 2.2 homework, we did what? We took a position function, you know, that s of t equals da 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 da. And what did we do to get the velocity? We took the derivative of it, and then we had the velocity where we could find, if this pin fell, we could find its instantaneous velocity at any point on its travel to the ground. If you fall from a great height, you don't just fall at the same speed. you accelerate. The further you fall, the faster you're going. And there's a terminal velocity, and it's got to do with air resistance and things like that. But the longer you fall, the faster you fall. It's not a constant rate. So if we take that position function and get its derivative, now we've got the velocity function. And then if we take the velocity function and take its derivative, which is now the second derivative of the position function, right? Now we've got how much it's accelerating. You can see where this could come in handy in physics, where you're dealing with acceleration.
I despised physics.
What's the famous F equals ma? That's one of the biggies in physics, right? Force equals mass times acceleration. If I've got a weight and I'm just holding it in my hand, the acceleration's zero. It's not accelerating at all. But once I start putting acceleration behind a mass, that's where inertia comes in and all those neat things. Anyway, long answer to a short question. Why would we want to do this? Well, here it is.
Yeah, you didn't believe it. Sorry.
Higher order derivatives come in real handy. And we're going to use them to tell whether a curve is concave up or concave down. Maybe where maximums are. You know, when you're doing pre-cal, we used the calculators and said, okay, here's a function. Let's use a function on the calculator to find a maximum, right? When we find a maximum, let's say, well, I've got a curve like that, and the maximum is right here. What's the slope of that line? Zero. So the tangent there at the maximum is zero. There wasn't any point in getting into that last year. But by taking higher order derivatives, I would know that that curve at some point is concave down. Handy. They come in handy. So, copy all these down. I'm just kidding. You can take as many derivatives as you want. Now, eventually, let's take something like this, x cubed. Let's say that's my f of x. What's f prime? 3x squared. What's f double prime? What's f triple prime? After that, what are my derivatives? Zero. And it remains zero no matter how many derivatives I took. So 3 is really as high as, well, 4 if you want to count the zero. So we could do that. And they're saying here, starting with the fourth one, just put a little 4 or whatever derivative you're talking about. Y'all, I've never gone past 2. Just because no calculus class I ever took needed it. Now notice we're going to be using 2 to get acceleration. Okay, let's look at a problem. Okay, so what are we starting off with here? What is this right there? What kind of function? In light of what we talked about. And maybe you're not picking up on my clues. It's a position function. All right? So I know if I get the first derivative of that, I've got a velocity function. So what would s prime of t be? Well, power rule says says 2 times negative 0.81 t. And then the 2 drops out because it's a constant. So I've got negative 2. No, scratch that. Let me see if I can multiply today. I've got negative 1.62 t. Now what's that? That's velocity. But I want the gravitational pull, which is an acceleration. So I'm going to take the second derivative of that. And I just got, that's pretty easy, negative 1.62. And that's going to be in feet. Now, if it was feet per second, that would be velocity, right?
Yeah, it is in per second, right?
But this is second derivative, and so I need feet per second, which is feet per second squared. That's the moon's gravitational pull. Now, Earth's a little bit more than that. It's minus 9.8. So it's asking for the ratio of Earth to the moon. So if you've got a calculator, I got a calculator real handy. Hold on. If I say negative 9.8 divided by negative 1.62, I get about 6.05. What does that mean?
Earth is 6 times more gravitational.
The pull of Earth is 6 times stronger than the moon is, which means, what do you weigh, Jacob Joseph?
I weigh 160 pounds.
All right, on Earth. 160. If I divide that by 6.05, 160.
Where'd you get 160?
That's how fat I am.
Yeah, you need to go on a diet.
Quit lowballing.
On the moon, he would weigh 26 pounds. Now, think about the ramifications of that. That means if he went to the moon right now, he's got strong legs, he weighs 26 pounds, he's got leg muscles that are used to moving around a 160-pound person. If he jumped, he could get to the door pretty easy. Because his leg muscles are only working a sixth, they're only lifting a sixth of the weight that they did. Right? Now think about this. What if you lived on the moon for a couple of years and came back to Earth? You're not going to be able to move. You know? You're going to lie in a puddle.